shifting graphs, new section. So we are going to shift or relocate graphs of equations in this section. So let's see how the authors start the section. This section shows how to change an equation to shift its graph up or down, or to the left or right. From this first line itself, we can understand one or two things immediately. The first is that because up and down, left and right, these shifts are available, once a graph is given to us, we can actually take it to any location through a combination of these shift operations. The second thing is that these shift operations will not achieve these following two things. They will not change the shape of a graph, that is, they will not change a graph. How the graph looks, that will stay the same. Where it appears, that will change. And the second thing, and the third thing is that these operations will not rotate a graph. So if you have, for example, a straight line, then a shift will not change its slope. Okay. Knowing about this can help us spot familiar graphs in new locations. It can also help us graph unfamiliar equations more quickly. This line can be understood using this simple example. Just for the sake of our understanding, we are going to first of all take a somewhat stupid example. Say one is very familiar with graphs like this, that is, straight lines passing through the origin. That is, one is very familiar with graphs of equations of this type, y equal to mx, where m is some constant. However, that person does not really know or has not really thought of the graph of an equation of this form, so y equal to mx plus. It sounds stupid that one knows about this very well but does not know this. Just for the sake of understanding, we are taking this stupid example to start our discussion. Now, how does one draw the graph of such an equation? If you go back to that process, what we do in the beginning, when we really don't know how the graph looks, we make a small table where we take some x values, permissible x values, that is, those x values that can be put here, which does not land us in trouble, and we calculate the corresponding y values. And these pairs give us coordinates of points in the plane. We plot those points, we join them, and that figure is the graph of this equation, graph of any equation actually. Now, if one encounters an unfamiliar equation like this, one can again go through this process of making tables, plotting points, joining them, etc. However, if one uses this idea of shifts, one does not need to go through all these things again. That's because one can recognize the fact that this equation is like this equation. The only difference is that there is a plus c. For the sake of being specific, let us take 2 here instead of taking an arbitrary c. Then notice that if this is your first table for this equation, when you make one such table for the second equation, taking those same x values, you can see that the new y values are 2 more than the previous y values. So naturally, because the new values are 2 more than the previous values, the new pairs will appear above the old pair. Say this is your y equal to mx plus c. If you put x equal to 0, originally you obtained some value of y, and that value actually in this case is y equal to 0. But now for x equal to 0 you will get 2. Like that, all the y values will be 2 more than the previous y values. So naturally, the new graph will look like this, which will be parallel to this graph but 2 units away and above this graph. So that's why without going through this process again, one can just recognize this fact and use the already known graph to draw the new graph. So that's how, if we encounter an unfamiliar equation, then we can draw its graph more quickly using the graph of a familiar equation. Now, this seems unnecessary for this particular case, that is these straight lines. However, situations arise quite often where it's not so trivial and unnecessary. It becomes necessary and it becomes useful also. For example, we have already seen that this equation x square plus y square equal to 1 has a graph which is the circle having its center at the origin and with radius 1, and we in fact called it the unit circle. Now if you encounter an equation that looks like this, then it's not obvious that this, I mean unless someone really knows about these things, it's not obvious that this also will have a graph that is a circle. One can without any idea about these shift operations and without having any insight, what would one do if one has to draw the graph? One will go through that process again, but one can use these ideas. That however, I mean there it was quite easy, adding 2. Here it is somewhat more complicated. That's why we need to learn about these things. One will see that this is also some circle. Its center is not the origin anymore. Okay, it is somewhere else. So one can draw the graph of this equation also from such a circle whose center is at the origin, but by shifting the circle properly. Okay, so let us now see how these shifts can be achieved. What do we have to exactly do to the equations to achieve these shifts? How to shift a graph? The first one is quite easy, and in fact it's the thing we have just seen in case of that straight line. To shift the graph of an equation, some general equation y equal to f of x straight up just like what we did there in that example, we add a positive constant to the right hand side of our equation, and we know why that will give us a graph that is shifted upward by that amount, that positive constant. That is because the y values are now more than the previous y values. And one example, the first example to illustrate this is here. Example 1. Adding 1 to the right hand side of the equation, y equal to x squared, to get y equal to x squared plus 1. Shifts the graph of y equal to x squared up 1 unit, because the new values are more than the new y values are more than the previous y values by 1. So we are now going to draw the figure, and in drawing these figures, of course, ideally we should draw the graph of this, actual graph of this, when we are going to draw this. But since the actual graph is not going to play any role, okay, in our understanding of this shift operations, we will just simply roughly draw the shape of the graph. That is enough for our purposes. Also, we will, for that matter, we will not be very careful about the scales. That is, how long is 1 unit on the x-axis or how long is 1 unit on the y-axis. We won't think of those things. We already know that the graph of this equation looks somewhat like this. Okay, y equal to x squared. So according to this prescription, this plan, the graph of this will just be this graph shifted up by 1 unit. That's all, nothing else. So if this is our 1, then this is the new graph. This is the graph of y equal to x squared plus 1. If you slide it up by 1 more unit, then you get the graph of y equal to x squared plus 2. If you slide it down by, say, 2 units, say this is your minus 2, then you get the graph of y equal to x squared minus 2. Okay, so that is the thing, you shifting up or down. And for that shifting down, clearly you have to add a negative constant to the right hand side of the equation, like this one, x squared minus 2, because then the new values will be smaller than the old values, new values of y. To shift the graph, of an equation y equal to f of x down, straight down, we add a negative constant to the right hand side of our original equation. Example 2. This is actually the figure for both example 1 and example 2. In example 2 we are going to mention this. So adding minus 2 to the right hand side of the equation y equal to x square to obtain y equal to x square minus 2 shifts the graph of y equal to x square down 2 units. Okay, so these vertical shifts are quite straightforward to understand. Just adjust the y values and you can get the desired shift. But what about horizontal shifts? How do you shift a graph horizontally? To shift the graph of an equation is same, just some equation y equal to f of x to the left side. We add a positive constant to x this time. Okay, let us see one example and then we will see why this works. Example 3, adding 3 to x. In y equal to x square to obtain y equal to x plus 3 whole square. Shifts the graph of y equal to x square left by 3 units or left 3 units. or you can write to the left also if you want, or left part, in any way you can write. And here also we can draw our figure. This is our original graph, y equal to x square. Now if you have the point -3, 0 here, then this will be the graph. Actually these two will not intersect. Okay, let me just draw it somewhat more narrowly. In reality these two will not intersect. I think that is the case. In reality these two, I am saying in reality these two will not intersect. No, that is not true. These two will intersect at some point, because we know that this separation keeps on increasing the further we go away from the origin. I mean, in case of this graph, the further we are from the origin, the further away this portion of the graph is also from the y-axis. So the same is true here also, because the shape has not changed, so they will intersect. I mean, the parts of the graph that we see here in this figure, they do not intersect. That's what I am saying. Okay, now let us try to understand why this is the graph of this equation. In the original equation y equal to x square, 0, 0 is a point. That is, the graph passes through that point. What do we get if we what do we have to put in place of x to get 0 y? Clearly -3. So the point on this graph corresponding to this point is -3, 0. And that's why you can see that because we had to put x equal to -3 in order to get y equal to 0, the graph has shifted by 3 units to the left, and that is why we add 3 to x in order to achieve this effect. If we add a negative value to x, then the graph will get shifted to the right by that amount, not by that negative amount, but by the amount equal to the absolute value of that negative value. For example, if you have, so this is the graph of the equation y equal to x plus 3 square, and here whether these graphs intersect in the figure or not, that really does not matter. The only thing that we have to see here is that they have got shifted. 2, 0. For this, the equation will be y equal to x minus 2 whole square. And this, of course, is the original graph. To shift the graph of y equal to f of x to the right, we add a negative constant to x in the equation y equal to f of x, like this one. Okay, so to shift towards the left, you add a positive constant. This may be somewhat more confusing than those vertical shifts. Okay, for horizontal shifts, you want to go to the left, you add a positive constant. You want to go to the right, you add a negative constant. Anyway, it is what it is. Example 4. Adding -2 to x. Oh, so example 4 is just this one. Adding -2 to x in y equal to x square to get y equal to x minus 2 whole square shifts the graph 2 units. To the right. And summarizing all these things, we have these shift formulas. Vertical shifts first, because that's what we saw first. Y minus k equal to f of x, or y is equal to f of x plus k. And what happens when one performs these operations is then written there. Beside that, which however we will have to write here because of lack of space. So much space in the universe, but we don't have enough space. And this operation shifts the graph of k units if k is greater than 0, and shifts the graph mod k units if k is less than 0. If you want, you can also say minus k units. And what about horizontal shifts? Here the operation is this: y is equal to f of x plus h. Shifts the graph h units to the left if h is positive. Mod h units to the right if h is negative. If you are thinking why you may have seen that often we use this modulus h, and even when it's known that h is negative, we do not seem to write minus h, although that is also equal to, that is in fact equal to mod h in this case when h is negative. The reason is that this is not just simply a number, but geometrically it represents length or distance from the origin, or we will see these things at some point, norm, which is a sort of a generalization of the concept of the length of a vector. We will see these things at some stage. Okay, that's why we write like this. In general, this notation is used, where what you have inside can be a vector in some sense. So this is the summary. Let's see another example. Okay. The graph of, so having gone through all these things now, how can we apply whatever we have understood to this equation? The graph of this equation, you can see that we in fact have performed two shifts, a vertical shift and a horizontal shift. To what? To this equation, y equal to x cube. If you add minus 2 to the right hand side of this equation, that means you are sliding the graph down 2 units. And when you add minus 2 to x, you are sliding the graph by 2 units to the right. So that means here the shift is like this or like this. So in the beginning itself we said that one can bring the original graph to any location. So combining two such shifts, one vertical and one horizontal, you can go to any place you want. So the graph of this is the graph is the graph of y equal to x cube shifted 2 units to the right and 2 units down. And B in fact no, okay, but before that let's write another thing. The graph of this other equation y equal to x plus 1 whole cube plus 3 is the graph of again y equal to x cube shifted 1 unit to the left and 3 units up. So for this second one, if this is our original graph is located here, say, then the shift will look like this. Okay, and here also there is a figure. We already know the graph of y equal to x cube, just like we know the graph of y equal to x squared. We have drawn these things in one previous section, where we in fact saw graphs of many different equations, not just straight lines, but this type of graphs also. The original graph looks somewhat like this. The graph of y equal to x cube. So if you perform a shift of 2 units to the right and 2 units down, that means the new location of the graph will be, so this is 1 2 1 2. The new location of the graph will look like this roughly. And for this one, so the equation of this curve, or the other way around, the graph of this equation y equal to x minus 2 whole cube minus 2 is this graph, and minus 1 1 2 3. So this is the graph of the equation y equal to x plus 1 whole cube plus 1. Do you really see how powerful this is? You already know the graph of this equation. Okay. If you use your ordinary formula of a plus b whole cube to expand this, then you see that this equation also looks like this: x cube plus 3x square plus 3x plus 1 means plus 2. So this is quite unfamiliar. Okay, it looks quite strange, and at once one may not be able to see what the graph of this equation is. However, if one somehow is able to isolate x in this way, okay, in this way means one can isolate things and see that the equation can be expressed in this form, where you get x plus some constant, a polynomial equation in x plus some constant, okay, plus something else, some other constant, then our job becomes very easy. So that is the power of this method. or for that matter you can expand that one also and see that you will again get a somewhat relatively more complicated looking cubic equation. Okay, next we come to equations for circles. And this time we are going to look at circles having any point as its center, not necessarily the origin. A circle is the set of points. In fact, they are writing the definition itself. All points in the plane, in a plane actually, whose distance from a fixed point in the plane is constant. Why I wrote a plane? You see, sometimes you see that in many other places, but particularly in the definition of a circle, that you see a plane, sometimes you see the plane. If you are studying 2D, two-dimensional Euclidean geometry, then it is unlikely that you will leave the plane of this blackboard, and it will not matter if you are drawing your circle on the blackboard or on the floor or on the ceiling somewhere else in some other plane. It will not matter as long as what you are studying is just the circle or some figures in that plane. So for the purposes of ordinary two-dimensional Euclidean geometry, one plane is sufficient. So in such cases we write the plane. However, if for some reason you have to consider a circle here and say another circle here in some other plane for some purposes, maybe you are interested in studying the geometry of a water pipe, for example, then different cross sections, if the water pipe is circular, if it is cylindrical with a circular cross section, you will get different circles. Okay, for such situations you may have to consider many different planes, because once you consider a circle, it lies in some plane, and that plane may be different if you consider cross sections at different locations. So in such cases we write a plane. The definition of the circle does not change, but it's just a it depends on what situation you are in. So that means once you fix a plane and you fix a point in that plane, then the circle is the set of all points whose distances from that fixed point is, these are all constant. Okay, same length straight line segments. And the definition of course does not end there itself. The fixed point is called the circle's center, TER, if you are following American English, and the constant distance is its radius. Is its radius or is called its radius. We saw in section 2 example 4 what did we see? That the circle of radius A and center at the origin 0, 0 has the equation x squared plus y squared equal to a squared. Okay, this we have already seen. Now if we shift the circle to place its center at the point say h comma k, then its equation means equation of the circle in the new location x minus h whole square plus y minus k whole square equal to a square. Let us try to understand why is this the equation of the circle in that new position. We can understand this in, of course, two ways. We can either think of this as a shift operation done to this equation or correspondingly done to the geometric circle, or we can use the definition of the circle itself to obtain this equation. See, we already know that the distance between 2 points in the plane, say you have these 2 points, one having these coordinates and the other having these coordinates. The distance between these 2 points is this non-negative real number plus y1 minus y2 whole square. We have already seen this, and how this formula itself comes from Pythagoras theorem. One can use this to obtain this equation. What one does is simply this. say this is your h comma k. We don't really know where this point h comma k is in the plane with respect to the axis, because we don't know what h and k are, or what their signs are, whether h is positive or 0 or negative. We don't know those things. The only thing we know is that it is some point, and say this is our circle with center at this point and radius a. Now if you consider a variable point px comma y on the circle, then the distance between these 2 points is constant. That's the definition of a circle. So the distance between these 2 points is this. Equal to a. Squaring both sides, you get this equation. Okay, this is actually the equation of the circle. We are saying that squaring it, we have got this. Can we go back? If we cannot go back, then there is a problem, because then these two equations will not be equivalent. If this implies this but this does not imply this, then maybe this equation represents some points which are not on the circle, maybe. However, that is not the case. And do you know why that is not the case? If you want to go from this equation to this equation, what will you do? You will take square roots to come from here to here. You squared both sides, so that means to go the other way you have to take square roots. So that means if you take square roots, the left hand side is okay, you get that itself, x minus h whole square plus y minus k whole square, and the right hand side actually is this. And we know from our study of real numbers that this is absolute value of a. Can we write this equal to a? We can, if we know that a is a non-negative real number, and it is, because we have mentioned that a is the radius of a circle, and radius is the length of a line segment which can be 0 or positive, but it can never be negative. So because of that, we get, when we take square root on both sides of this equation, we get that equation back actually. So writing this or this mean the same thing. And in fact, we often don't bother to say these things because they are understood. But if one does not know why they are equivalent, then of course that person will be in dark. Okay, so this is one way of achieving the equation of the circle. But can we think of this entire thing in terms of shift and those? Okay, for that, what we do, we start with our original circle, which now again has radius a. Radius is a, but now the center is 0, 0, and its equation is this. Say your new, for the sake of simplicity, your new center is going to be here. For horizontal shifts, we know that we have to, if we want to shift it to the right, then we have to add a negative constant to x. So here we have added a negative constant to x. Negative constant because h is positive. But what about y? The rule for vertical shift seems to have been given only for equations of this type. Okay, you add a positive constant to the right hand side, your graph goes up, add a negative constant, it comes down. However, you can clearly see that the equation does not have to be like this. The equation actually can be of this form also. Here itself you can do those shifts. You see, when you add a positive constant, say k, the graph goes up like what we need here. However, equivalently, instead of writing like this, what you can do is you can add a negative constant to y itself. That will also give you the same effect. In fact, when we summarized all those shifts, vertical shifts, horizontal shift, we mentioned this we mentioned the shifted equation or the changed equation in this form also. So if you do that along with the horizontal shift, you get this. Okay, so you can think of obtaining the equation of the circle in this form using shift operations also. Okay, that is fine. So let us now see some examples. And these examples will involve circles. So this is going to be example 6. If the circle is shifted 2 units to the left and 3 units up, x square plus y square equal to 25 is shifted, what did I just say, 2 units to the left. Three units up or down? Up. Its new equation will be, okay, let us see if we can really write the equation down. 2 units to the left. For shifting to the left, we have to add a positive constant to x, and 3 units up. 3 units up means originally in that form of the equation y equal to f of x, we had to add a positive constant to the right hand side, or equivalently you can add a negative constant to y, and that's what we are going to do here. Y minus 3 whole square equal to 25. X plus 2 whole square plus y minus 3 whole square equal to 25. So you can see that using these shift operations we have been able to, geometrically of course we can imagine that here we have a circle and we are shifting it here and they are getting new locations and those things. But algebraically now also we can think of those things. Instead of going through the painful process of transformation, between these algebraic equations and the geometric figures. And that transformation is nothing but the process of drawing the graph. So we don't have to go through that transformation. We now know what happens, whatever happens in the geometric world has a corresponding change in the algebraic world, in the world of equations. And now looking at the geometric world, which is very easy to visualize, we can figure out what happens in the algebraic world. Example 7. The standard equation for the circle of radius. The standard equation for the circle of radius 2 centered at the point 3, 4 is just what we, this one, x minus 3 whole square plus y minus 4 whole square equal to radius is 2, that means 2 square or 4. Okay, so this is the standard equation. Oh, so this is just one example showing a specific circle with center that is not the origin. There is no need to square out the x and y terms. Yes, this is also another important point. Not related to, well, I should not say not related to whatever we are going through right now. You see, the thing here is that going through school algebra, we get the habit of always expanding things. Whenever we get a product, we have the tendency to multiply terms out and write the product in its most revealing form, if I want to say it like that. Just like that, when you see a power like this, we want to expand it. Okay, without even thinking why we are expanding, we have got the habit of expanding from sheer practice. But in this case, that will not help us at all. In the present form, this equation tells us that the center of the circle is the point 3, 4 and the radius is 2. But if you expand the terms, then the things will get lost. So that's what they are saying. There is no need to square out the x and y terms. In the above equation. In fact, it is better not to do so. the equation in the present form reveals the center and the radius. Then there is another example which is in the form of an exercise actually. 8. Find the set. Okay, I need ink before I write something. Find the center and radius of the circle x minus 1 whole square plus y plus 5 whole square equal to 3. So because this is a question, there will be an answer. Solution. Comparing the given equation, this one, with our standard equation. We get h is equal to 1, k is equal to minus 5 and a is equal to square root of 3. So the center is, we know that the center of this circle is h comma k. So correspondingly the center of our circle is 1 comma 5 and the radius is square root of 3. Okay, then in the next example, that situation occurs about which we were talking, that an equation may look very unfamiliar, but it will turn out to be the equation of a familiar curve only if we think of it in terms of shift operations. Or in this case, if we can express it, it's going to be a circle if we can express it in this form. This one also is an exercise, and in fact it has been mentioned that this is a circle. We are being asked to find its center and radius. of the circle x square plus y square plus 4x minus 6y minus 3 equal to 0. So we start with the given unfamiliar equation. Which is equivalent to, okay, so now what we do, we try to create these square terms here on the left hand side. On the right hand side, we will, whatever we need here, we will need something extra here. In order to create those square terms, we will adjust them on the right hand side. So to get square term, we take x square and we take this x term, which we write as 2 times x times 2. The strategy is to somehow be able to use the formula a plus b whole square. So we are creating a situation for that here. So you can see that one term you have already got, you have x square, but then you have 2 times x times 2. Now if you have 2 square, then that will give you, that is, if you have plus 2 square, that will give you x plus 2 whole square, but you don't have that. So that is one extra term. Plus we do a similar thing with the terms involving y square minus 2 times y times 3 plus 3 square, and here we have minus 3, and 2 square and 3 square are extra, so we have to add that to the right hand side. And that is equivalent to this. First part becomes x plus 2 whole square, x square plus 2 times x times 2 plus 2 square, and the second part becomes y minus 3 whole square. Now this becomes 4 plus 9, 13. 13 oh, that will become 13 plus 3, because if you add 3, it will become 16. So you can see that this is very conveniently 4 square. Comparing this last equation with our standard equation, now h is minus 2, k is 3, and a is 4. So the center is h comma k, that means minus 2 comma 3, and the radius is 4. So you can see that this very unfamiliar looking equation, if you draw the graph of this equation, it is going to be a circle, and that too not just any circle, this circle whose center is at this point and which has radius 4. Yes. We will now extend the scope of these things slightly by defining interior and exterior of a circle, okay, which will turn out to be graphs of inequalities. We have already seen graphs of inequalities. They are regions in the plane. So these are also some particular regions. The points that lie inside the circle x minus h whole square plus y minus k whole square equal to a square are the points less than a units from h comma k, that is the points which are inside. A figure would be useful here. And the figure, there is in fact no need to use ruler also. So this is our circle whose equation is this. This is the center h comma k and this is the radius a. Now if you have a point inside the circle, you can clearly understand what we mean by inside here. Then the distance of that point from the center is less than the radius. That's what we mean when we say the points that lie inside this circle are the points less than a units from h comma k, that is their distances are less than a, and they satisfy the inequality x minus h whole square plus y minus k whole squared less than a square, and they make up what we call the interior of the circle. This region, okay, this region is called the interior of the circle. Note that no point on the circle is in this region, because any point on the circle is at a distance exactly equal to a from h comma k, not less than a. Like that, there is exterior. The circle's exterior consists of those points that are more than a units from h comma k, that is they are outside the circle everywhere. That outside, that unbounded region, we are using these terms interior, exterior, unbounded very loosely. Okay, by them we mean what you understand them to be, nothing else, nothing more technical, although these are technical terms in mathematics which are more than a units from the point h comma k. These points satisfy the inequality greater than a square. So this is interior, this is exterior, and this curve is the circle. So you can see that the circle divides the plane into three distinct parts, namely those points that lie outside of it, those points that lie inside of it, and those points that lie on it. There is one example 10 involving these notions. Okay, and one more thing is I should perhaps write the inequalities here also. Plus y minus k whole square less than a square. One can say that this inequality represents the exterior, or the graph of this inequality is the exterior. Like that, the graph of this inequality is the interior, the bounded region inside the circle. Inequality and the corresponding region. If your inequality is this, then the region is the interior of the unit circle. If your inequality is this, less than or equal to 1, the unit circle along with its interior. If we continue from here, if your inequality is this, then the corresponding region is the exterior of the unit circle and if your inequality is x square plus y square greater than or equal to 1, then the region is the unit circle along with its exterior. After this we have parabolic graphs, which however we will see in the next calculus video. These terms, interior, exterior, boundary, although we haven't said anything about boundary, these are technical terms in a part of mathematics known as topology. It's a very fascinating subject, although I would not suggest you see this, at least skim through the things of topology. Now itself, I would not suggest that. Things will very likely go over your head. Maybe I will tell you something about topology when we go to continuous functions. Okay, then you may be able to understand at least some preliminary ideas. So I'm going to end this video here itself. As always, you can comment in the comment section below. Tomorrow we have Gregory-Tilly's algebra exercises. Day after tomorrow, analysis, and on Monday, number theory. So because on Monday we have number theory, there is no need to write or say what is going to be the next video in the usual cycle. Is there anything else? No, I think that's it. So see you in the next video. This is me, Lucifer, from A Mathematical Room. Have a nice night.